Okay, we are going to talk about score matching. This will be a transition from energy-based model to diffusion models. So score matching is based on the ideas that we do not really need the energy when you do the sampling. If we do score, that will be sufficient. It can also be used to train energy function. So it can either be used to train the score or because derivative of energy is a score. So you could also use that to train the energy because using this relation. Yeah, generally speaking, score matching itself is another unnormalized learning methods. You don't need a normalization constant unlike a maximum likelihood estimate. It's similar to this NCE. So the formula is exact. You could, and there's no need for proposal distribution. So from that end, it's naturally closer to what we have for the unnormalized. But you know, it has certain issues if you just directly apply that and try to generate using these. So in the end, it evolves into diffusion model, which is much more efficient but closely related. So especially the denoising score matching is very similar to denoising model. Denoising model using denoising score matching as well. Basically, denoising score matching means score matching has an interpretation of denoising. So that's what we want to talk about in the second part of the lecture. But we will start with the first, the standard score matching. So, and then we will tell the difference. Okay, so the background, again, you know, we want to do the unnormalized energy models, right? You know, we already talked about that. It's harder to sample, harder to train. MLE is a standard way to training energy-based model using contrast divergence, but it's only approximate. On the other hand, we know score-based Langevin generation can be used for sampling. So as long as you learn score, that's sufficient. So this is one of these reasons you can do the score matching. So basically, the idea about this score matching is this matching model score to data score without computing normalization. Score itself doesn't need. So therefore, as long as you can find the equation involving score optimization, then it doesn't need to do normalization. So this is objective we want to establish in the first part of the lecture, such that score can actually satisfy a optimization problem, which does not need normalization. However, there is a drawback for this kind of optimization. As we will see, it actually depends on the derivative of the score. So this derivative of score is harder to implement in practice. We show one implementation exact, but there are some approximate. But eventually, you know, this is the one reason, and it's not used as widely. And denoise score matching actually address that problem. So basically, you don't need the derivatives. You just need a regression problem, which is very nice. Yeah, so implicit formula is how you derive this. So we give that. This needs some calculus, but generally, you know, we will go through the derivation. But as long as you know there is something, the relation is good. Yeah. Yeah, denoising score matching is yeah, it's basically we'll show that. We will show that basically later on. Yeah, so denoising score matching. Okay, so this is essentially the outline. So how do you derive score matching, the optimize objectives, and the denoising score matching. which becomes a regression problem. The score matching itself is a different optimization. Also, it requires a derivative. De Noisy score matching doesn't. So that's the summary. So let's look at that, right? So just recall last two lectures, we talked about energy-based model. Energy-based model, of course, I mean, we keep mentioning this. So we already mentioned this a few times. So this time probably, you just say Z will be harder to compute. This partition function, normalization constant, which makes it challenging. So you directly, right? And maximum likelihood estimate, of course, that's from the last lecture. It includes Z. If you remember, the gradient of maximum likelihood estimate involve expectation with respect to the current model. You either sample from the current model without normalization, or you have to, usually that's only approximate, right? So basically, the optimization is difficult. Gradient dependent model expression requires sampling, that's also difficult. So yeah, so basically, this we see actually for if you remember the example we give, we have a few methods last lecture. The longeving for the sampling, right? This is doing maximum likelihood is probably the most expensive. You need a lot of longeving runs in order to do this. But you could also apply other MCMC method, which we didn't talk about. The original contrast divergence paper, they use others, like deep sampling, like other stuffs. But anyway, the other thing I just want to recall, which is related to score, right? This is a score, so a gradient of F. So for continuous data longeving updates, will only require this guy. This is the only thing you need to know is this score, right? You don't need to know F. You only need to gradient of F. So that's is sufficient for sampling. Score, if you recall, we talked about the two lectures before. It's a gradient of F, but it's also gradient of log of your probability with respect to your data, not with respect to the theta. Sometimes, when you look at when we actually look at the policy gradient, right? So we do have a log of probability, which is a gradient to the theta, the model parameter. Here, the gradient with the data, which is y. Okay, so this is called a score. Yeah. So important observation. We do not need the normalization constant, right? So when we do this, because it's when you take derivative, normalization constant doesn't depend on y, only depend on theta. When you take gradient with y instead of theta, it gets rid of that. So basically, this is the reason we only need a vector field, this score, for the sampling, if you use the longeving. So let's look at how do you try to learn that. So that's the key things which we want to go through that. Can we learn that directly, right? So this one. The answer is actually yes. So that's interesting. That's a very nice observation. It's a non-trivial observation, I would say. You can do that, but it's not hard if you know where to look for, right? But essentially, this is essentially what the answer is. Yes, you could do that. If you can do that, right? So you don't need the normalization first, and both for training and for the generation, because you just run longeving, right? The other thing I want to say is the following. So you could plug, if you say I can learn this guy, right? I can also plug in this guy to directly learn. This guy is a gradient of F, which is directly learning the energy, because this involves F, the gradient, right? If you learn the gradient, you hopefully can learn F. So it's actually can be regarded as unnormalized entropy, but the focus is more on learning score in our case rather than learn energy, right? We talked about learning energy last time. There are three methods: two approximate, one exact. and they all have problems, right? So if you think about that, so they are not perfect. This one, they also have issues, but a different set of issues. There's no proposal distribution, so you don't need to worry about what kind of GAN-like issue, right? Discriminator is too powerful. But here, the main issue is we will talk a little bit about that later in the end, and then where the diffusion model will not have such issues. So avoid the expensive partition function estimation. So that's another thing. Yeah, basically the method is called score matching. So, and we will see next what it does. There will be involving some math. So we will first 2 slides just talking about what score matching is, right? Score matching is coming from, yeah, this paper. So, so it's kind of compared with the whole field of statistics, right? If you think about the energy model, if you think about the maximum likelihood, that's statistics. That has been around for many, many, many years, right? But score matching is relatively new. If you think about it, it's roughly 10 years ago. So it's not as old. You can learn the score, gradient of f. This is basically proposed in this paper. So this is the definition of a score. And what is actually objective function? So let's first look at their objective function, and later on we will say what it becomes, right? So this is the objective function, which is trying to do with a score matching. Here, actually, yeah, yeah. Here, okay, actually, this is just for the objective function. So we will show that soon. So there are 2 slides talking about this. This is a real score. That's what you learn, right? This one is just for convenience. This one is actually used in the first objective function, but it involves something you don't know, right? You don't want to have a gradient of your data score. Basically, score matching is matching this guy to this guy. But this one involves something with a data score, right? Data score you don't need. So basically, this is just for theoretical motivations. The algorithm itself really doesn't need that eventually. So this is what we want to see. Yeah. So here is the objective. Objective is this is the empirical data from observed data, right? So from the data, you sample. This guy means you just looking empirical samples, taking average of your model score minus the data score. This data score is unknown, by the way. We just mentioned that. But we start with this. At this point, we have something unknown, which we want to get rid of, okay? But this is the objective. Eventually, what happens, we will see after some calculus, this one can disappear, okay? This is later on we will see. But then you introduce a gradient of a score to make that happen. But here is objective, which is natural. Essentially, it's say, oh, if my score, right, matches a data score on every point I draw the data, then I learn this well. So basically, this is what it is. So model matches the data everywhere, right? Then under suitable conditions, model density matches. These suitable conditions we will not talk about. This actually is one of the issues with score matching, which lesser issue is with diffusion model is if you have a very isolated modes, right? Isolated modes, actually, if you are taking gradient, there's a part of the which really not differentiable. So isolated node is not friendly to score. They can have a different weights of the modes. The weights of modes will not be determined. So basically, but if you say I don't have isolated modes, I have all connected, all these, then score matching actually is okay. Yeah, essentially in the informal sense is say this distribution has to be connected. You don't have isolated modes. Yeah, then you are then once you learn the score, you learn the whole distribution. Okay. We will not talk about these details. We will just probably make some comments later on. But before that, we just look at the key part is we want to solve this optimization problem, except this is unknown. So this is something we want to do, want to address. Before I address that, I will just say what this function is. We will quickly mention that. So the function, this objective function is so-called Fisher divergence. This has a name. It's a distance between two data distributions. If you say I have a data distribution, right? I have this objective, then this is called Fisher divergence. This is just the name of this distance. So if these are identical, this is 0. If they are different, usually they are not 0, unless you have some special cases, as I mentioned. Compare with KL divergence, right? So these are looking at MLE or MLE. If you know that is a tail of data versus p theta, so you're minimizing that divergence when you do the maximum likelihood estimate. But when you do this score matching, you minimize this divergence. Right, and there are some relations of these two again, but those are very mathematical. So different conditions basically say, oh, this divergence is small, then KL is small, versus KL is small, this divergence is small. Those are require certain conditions to say, this distance, which distance is tighter or whatever. But we will not. But loosely speaking, typically, I would just say KL is a more strict condition. Essentially, it's a tighter condition means it's harder to satisfy, right? This small usually doesn't mean this is small. This small usually, I mean, this is just loosely. It's not strict. Yeah, it's a little bit more stronger condition here. This one, you just say it's a little bit weaker. This is just loosely speaking. So let's look at the key observation, right? The score matching can be rewritten. So this one is coming from this Fisher. This one again is, remember, it's Fisher, right? It's coming from this differential. This difference. SQ theta is a vector. Score is a vector, right? D-dimensional vector. It's an I component of vector, and taking gradient with I. This one is I's gradient, and you do that. Plus this term. This term, if you do expansion of these least squares, you see this term. So basically, it's coming from this term. And plus constant. When I say constant here, it's just say it's independent of the theta. Right? It could be dependent on y, but it depends on or data distribution. So this is actually where the data distribution comes in. So you have a data distribution here. But this data distribution, because it's a data dependent, it's not theta dependent. The same thing happens in the KL. KL, when you do the minimization, part of that is you just become log loss because you also remove one which is data dependent. So this is a curve. Make it you can replace this by this guy. And this guy now we know we can solve that because this one I just replaced with summation. And here you have additional differentiation. So this is a formula. We will give derive, but the derivation itself is not necessarily required. It just so there's a it can be done. That there's another differentiation. So when you do the score matching, the standard, and this can be approved by integration by parts, which we will go through next time, and then the next slide. Yeah, here basically you just say this guy is this guy, right? So this guy, and the gradient of this is this. Basically, just says the definition of that is gradient of I is this vector to do that. The other way to say this one is divergence. Sometimes they call this operator divergence, and then this one. But there's doesn't need S theta here. S theta is coming here actually. It will become here, but because there's no interaction with theta, so it's fine. Okay. So basically, we will try to prove that quickly. just as just the exercise of calculus. So let's give the proof. This is just for the information only. It's if you don't remember the calculus anymore, it's okay. It's not something we just you just know where it comes from. So this is our objective. These are 2 times of our objective, right? So S minus theta, which is the score matching over the data distribution. This is just the expanding of these squares by these squares, this correspond to these squares, right? These squares correspond to these squares. This becomes constant. And now there's an interaction tip, because this, when I say constant, means this doesn't depend on theta, right? We are thinking about the optimization problem with respect to theta. Any theta independent component is considered a constant. And A is where the interaction of S theta and S theta, right? This thing we don't know, right? So at this point, this guy we do not know. So we need to get rid of that. So and there's a simple trick. This is A call. So I will just say, how do you get rid of this guy? Here is the simple trick. A is this guy, right? So now you do have this thing. You do have this unknown stuff with the data, which you cannot compute. Then what you do is you are writing this. This is basically just rewriting this guy as a vector inner product, right? This is ice component. This is ice component. This is just by definition. So then what do you do, right? So this guy, right, and then what you do? So here, right? Here, actually, what you do is similar to policy gradient. So if you remember the policy gradient, we say a little bit. So log of this guy, when you take a derivative, is 1 over p times log of gradient of p, right? 1 over p will cancel this. So this is how it does. Yeah. This coming from log of p, taking gradient, is 1 over p gradient with p, okay? And 1 over p cancels this one p, so then you just have this guy. So basically, this is just the derivative formula, calculus. Another calculus is this, right? So it is this guy. This is an integration by part. Basically, it's moving this guy, gradient, to this side and taking minus. Assuming the boundary, usually, probability, you have 0 in the infinity. So boundary condition is you have a 0. And assuming this boundary vanishes, S times P, and then essentially this guy is this guy. Minus, you move this gradient to this part, okay? And then you evaluate the product of these 2 terms in the boundary. Boundary will be for each is minus infinity plus infinity. You assume S times P is 0, okay? Because P usually vanishes at 0. You can think about Gaussian. It's vanishing exponentially. So essentially, this becomes this. And this is actually come back to the desired formula. So this one is already this formula. The formula is you plug that in, and it's this formula. Okay, this one basically gets you the derived formula. You can plug that back in. Is what you want, because this one taking gradient of p becomes taking expectation with p. So this is this is basically the math derivation using calculus. Okay. And it's not too complicated. You just need to remember your calculus and remember this integration by parts, and then you can do that. This is not the focus of this class, but we provide here and go through these ones just for your information. So basically, where this comes from. Once we have that, we can move on to the to how do we want to implement this method. So when we want to implement, right, we look at the sample version, right? We see the samples and we minimize the empirical objective instead of the expectation objective of this guy, right? This one is the case that you have n samples. This is exactly what you do. So you have some smoothing condition on your score, and then you're optimizing this score, right? So basically, this is a formula which you want to optimize. You optimize. Equivalent, the convenient way to say this is called divergence I mentioned. So the other way is to say instead of doing that, you do the divergence. So this is just a notational issue. It's just say divergence of a vector field is a gradient of that sum for each component. This one coming from the physics literature. When you look at the physics like electronics, like yeah, they all have this called divergence, and this comes in. But basically, yeah, here is a sample version. So we just focus on this guy, right? Divergence is just notation. Once we have that, we can try to implement, right? The implementation of this one, when you have a very large, you use some specialized samples. When you have smaller dimension, as we will in our example, we will use some exactly just taking derivative using PyTorch, right, to do that, right. So one thing, of course, is derive a high order derivatives. These just comments. So these are unusual compared with maximum likelihood estimate, right? Maximum likelihood or regression, they never take the derivative in your objective. Here, the objective has the derivatives. There are some other formula in machine learning, like in some they also require derivatives. So this is not the only one, but this one definitely stand out. It needs a derivative rather than most of that doesn't. Usually, once you require derivative, it becomes more complicated. It just becomes trickier. So people try to avoid that, but it can be done. So score matching avoids normalization, but introduces new requirements. If we parameterize the energy function, right, then the score is induced by structure, this guy, right? And the score matching then become a second order derivative of this guy. So you actually require, if you are thinking this is your parameterization, this is a vector field. This one is a scalar field. So you do have a smaller, but this one, if you use this guy and using another derivative, so this one becomes second order derivative with respect to f. Or if you just do that directly, it still requires a first order derivative. So basically, in both cases, you need a derivative. You could either parameterize by f, parameter by the s. In our case, we will do that, parameter by s, right? And then but basically, you have a second order derivative or first order derivative. But basically, yeah, you always have a derivative. And let's parameterize by s instead of the energy function. S is the gradient of energy function. We do not impose other structure. We just say it's a vector field, right? Score matching loss. Here is how it's computed. I mean, this is a training loop. Your PyTorch, right? This one basically you calculate score matching loss, your optimizer, your backward, and your step, right? So this is pretty standard. This one just say how the loss is computed. Loss you start with this is a score. This is a vector, right? Basically, they will dimension is your output. In our case, we have a simple example. It's just this is a score, and this is a divergence. They go through all this shape of y, which basically goes through all the dimensions, and you first calculate this torch gradient, right? So basically, this is a gradient with respect to the s component, right? So yeah, basically, you retain the graph, computational graph, so that you don't need to recompute a lot of things. Otherwise, you have to create a lot, recompute each of these autograd. But if you keep the computational graph, remember we showed before each variable, each computation, you have a dot gradient and so on. And then it's a safe. It's not too bad computation-wise. You just do each computation, and then you summation that, right? This one becomes your divergence after this loop. After this loop, it's just summing over the derivative of all. If you have a d dimension, this requires d. So it's actually, d is large, it's pretty expensive. So people try to approximate this. We will not talk about that there, but if you're interested, you can check that. So in the literature, people do that. But this is exact derivative times 0.25. This is a score. This is a score, right? So this is your objective. Once you do that, you can actually learn score field. So essentially, yeah, this is as we will see the example. Okay, so let's look at the example now concerning this implementation, right? So this implementation not too bad. Look at it. If you look at this implementation, once you have a PyTorch, once you have an AutoGrad, it's not too bad. You just need to put in this grad as part of your loss, and then it automatically take basically, PyTorch will automatically take the derivative of derivative, right? So here you already have a derivative. Therefore, in the PyTorch, it will have another derivative, right, for that. So, but this one is done automatically, so you don't need to worry about that. So basically, this one can be done. So once you have this score, you could just using Langevin, right? So this one, again, in our examples, we just use this vector field. We do not consider this coming from this guy. So it just this directly. Once I have this score field, we just run Langevin dynamics, and we can approximate the direction, and it becomes useful for generation. Even if this guy is unnormalized, in fact, you don't need the energy function, you just need the score. So that's another thing. And in diffusion model is similar. So you could model that as energy gradient, but you could also model that as score. So we are actually most implementation in the diffusion model only also looking at the score field only. They do not look at this part, which makes it simpler. Yeah, make implementation simpler. This is the same example we did the last time. So the example we did was 2D mixture of Gaussians, right? So you have, again, you have this one, you have this one. So if you look at the last time, we have something called proposal distribution, right? Which is covers this is a zero mean Gaussian. Here we don't need that. So if you think about if you need the proposal, it's probably for the Langevin, right? It's not for the estimation. Estimation itself in the score matching doesn't need anything like proposal. Yeah. So we have MLP, just simple score. Again, this score is energy. You have a one dimension, right? It's a scalar. For the score, because this is a two dimension, you have a two dimension. This one is also two dimension. This is a vector. Score is a vector. Okay. But it's MLP, right? So basically, the first, the second, you just have two outputs. So that's pretty standard implementation, as we probably all have been done training with the score matching loss. Score matching loss coming previously, right? So that's the implementation. And the string loop is it's a short. It's not very difficult. And then you say, okay, can we learn a score function, and can we run this field? So this is basically the what do you want? Yeah. So we generate by Langevin dynamics with the learned score. So this is something. Here is what you get. Yeah. So first you get this training curve. So score matching, the loss actually goes down. So that's good thing. Basically, you are actually minimizing. So here is in the end, because we know in this case we do know the S data, right? The algorithm doesn't need to know, but because we have a simulated data, right? So we do know S data, so we could compute this guy. You just say, we start with this one, say whatever, zero, whatever, but this one is large. But after this optimization, this number normalized the score, right? It's 0.04. which means it's a reasonable optimization, right? It's going down and essentially becomes this. Okay, so this is just looking at this one. So this is not too bad. Basically, you do converge. So for this kind of score matching methods. Yeah, I think I put a little bit of regularization, which if you're interested, because the notebook is provided, you can take the notebook. It's you need a little bit of regularization saying the S is smooth or whatever. Yeah, but those are those are the things you usually add in addition to this. We always adding smoothness to the neural net models, right? Just here is what you see from the generated samples, right? And this is the data, which is, and it's reasonable well. This is using Langevin and the learned score field and Langevin to generate samples. It's not too bad if you look at that. It's actually pretty well. Actually, it turns out for this simple problem, this one does better than diffusion model. So we will see diffusion model generate, for this kind of simple problems, it doesn't, somehow it's a little bit, this one actually does a little bit better. Yeah, so for that. But for the more complex model, things will be different. Well, one thing I think I a little bit mentioned, right? So although this looks good, in reality, because you have a two isolated, kind of a more or less isolated mode, typically what happens for the score matching is score, because it only take a gradient, right? The proportion of this guy is it's a little bit not sensitive to proportion of this guy. Say in our case, maybe it's half, right? But for score matching, usually it's a little bit difficult to adjust the proportion. Basically, once you take the gradient, this one is closer to 0 or whatever. Then essentially, the ratio of these two can be changed. So so this is usually which is different from KL. When you do have a KL distance, when you measure this KL is small, right? This two ratio usually is preserved, has to be small as well. But for the score matching, usually because it's taking gradient and there's a constant scaling constant somehow is less sensitive. So this one can change more. Yeah, basically they just want to make comment. And this also one issue about a lot of different modes. You have a lot of different modes. I think I mentioned in the Langevin lecture. So Langevin has some problems discover all the modes. It can be unbalanced. And the score matching will be similar if you just do that in this particular space, rather than in the diffusion model setting. It's become better because diffusion model starting from a very smooth distribution, gradually making it sharper. Then that gradual making it sharper get is better. But if you're just working with this kind of sharp distribution, with a lot of modes, if you say instead of 2 modes, I get 5 modes, then become more and more difficult to balance all the modes for score matching. Okay, so this is actually one of the issue of that, which making it more useful in practice. And a similar issue with Langevin, so making it more underscore somehow the theory about diffusion model making it much more robust to this kind of situation. So yeah. Of course, when we do image generation, there are different modes, right? Like different conditions. You have a tiger or you have a horse, right? Whatever the different species, and then you have to generate different things, and those different things will be different unique modes. Those modes are easier to do with the diffusion model. If you do this guy, things like mode collapsing, like GAN type of stuff, or can easily happen. So yeah, basically. These are comments I want to say, although we didn't show that here, but I just want to make a comment so that one later on we talk about the diffusion models, we know what is strong. Yeah, I mean, otherwise, if you are saying diffusion model versus let's say this kind of a score matching, right? There are other differences, definitely. For the generation, diffusion model also is a little bit simpler. They are not using Langevin, they are using related, but also, but somehow, but I think this is the quite of a main part. Yeah, the mode, how do you track the modes from this setting of diffusion. But we will talk about diffusion next class, so we'll talk about that. Here is the learned field. Again, you know, so this is a true field from the gradient of energy, true energy, right? This is the learned field. The learned field, I just want to say, I didn't put a constraints, right? You just have this score, right? Score is a vector field. And but you know, it gets reasonably well. For this kind of situation, it can be much more harder to learn because these are low density situation, right? So, but still, generally, it's kind of not unreasonable, I would say. It's not quite the same if you look at it. These are all straight here, right? This one is starting to be curved. So essentially, you do see. This could be because of a regularization condition and so on. So we do have some regularization condition. But nevertheless, overall, especially in the high density region, it looks good. So that's where it counts. Right. So basically, this is example. Okay, so let's try to move on to the denoising is more important to some way. People moving away from score matching to denoising score matching, and you can always use denoising score matching to replace. In this lecture, we use a denoising score matching to regard as approximation of the true score matching. But in the diffusion, they just directly using denoise score matching. There's no even know about original score matching. So we can formulate the score matching a different way, right? So related to denoising, and it's equivalent to denoising. We will see one interpretation of a score in the denoising setting is a denoising direction. So that's actually interesting, right? So basically, and you're keep denoising. This is where the later diffusion. It also avoids explicit derivatives. So your training become object regression problem. If you think about all the generative models, right? Just thinking about that. I mean, this one is one of the, and certainly diffusion model is a diffusion model. Of course, is a successive denoising. So people probably know that, and then it's training is a regression. So it's easy. If you think about all the generative model, right? So you are saying GAN. GAN is not regression, it's minimax. It's more complex. Thinking about, I mean, like a maximum likelihood, right? Complex, right? Or even you just using this kind of NCE. NCE is a little bit like a GAN, but you have a proposal, which, again, you know, it's not regression. So that is not too hard because it's a binary classification, but the proposal can be challenging to get it right. But if you look at this denoise score matching or diffusion, they started regression. Regression is much simpler. So this is a very attractive. Learning becomes easier. So which means the learning becomes easier. So that's another thing. Yeah. This is the paper itself connecting to the denoising autoencoder. But you know, in our case, probably just a denoising process or denoising in diffusion. Yeah. Score matching is a very interesting paper, nice paper connection. It's a short paper, but you know it's give you very explicitly to tells you what score matching and denoising, and especially you have a Gaussian denoising. You can add other noise. Actually, even other noise, we will state the general one with all the noise, but then we'll specialize for the Gaussian. So let's look at that. This is a part we can go a little bit slower here because you know just try to understand it. It's not, again, it's not too hard. It's a little bit easier than the score matching because score matching needs a partition integration of parts, right? So but here you don't need, you also need some calculus, but then it's simpler. Start with a clean data distribution, right? You add noise. This one just say Gaussian noise, but generally we can say this one is more arbitrary noise. Okay. For now, for all the let's say for all the diffusion model, they all just add Gaussian noise, right? So let's say we add Gaussian noise, but generally you can add other noise as well, or generally you have to say. So here is the noisy distribution. So this is original data. This is noisy data. And then you look at the noisy distribution. Denoising score matching can basically, it's simple to say that denoising question says this guy can be learned by the score of this log of p gradient can be learned by regression. Just using this setting up a regression problem. So that's conclusion. Yeah, it's a score of the noisy distribution. It's not a score of the original data distribution. But because if you set sigma is small enough, right? If you think about sigma small enough, then original distribution score and the noisy distribution score become very similar, right? Then you are saying you approximately learn the original scores. Yeah. So original, if you just want to exactly learn this guy, the scores of this guy, you go back to the score matching, right? But the denoising score matching say, let's do a denoising, have this guy, then we have a very nice formula for the score of this guy, which can be expressed by regression problem instead of this kind of weird Fisher optimization problem. And there's no derivative needed, so linear score. So basically, yeah. So this is set up for the noise. Then what we want to do is doing the following, right? Yeah, so yeah, basically this one is the comments to say is learn score that. So you have to understand original distribution, noisy distribution, denoising score matching learns the score of this guy, right? If you want to connect this to this guy, you to the sigma small enough so that they are approximately similar, right? So okay, so this is basically the relationship about denoising and original score. And if you only want to learn this, again, the only thing you can do is going back to the score matching, not denoising. Denoising score matching is approximation. So let's try to do this guy. Here we want to state as a more general. It's beyond the first formula we want to do. Derive the denoising score matching formula is beyond the Gaussian noise. It can be arbitrary noise. Then we will specialize to Gaussian noise. The score we want is this guy, right? So this is a score of your noisy distribution. So what do we do? Here is the formula. So first, I will take a gradient of this guy. Eventually, gradient of this guy is a gradient of this guy divided by p, right? We know this gradient of log p is a gradient of p. Then later on divided by p. Okay, divided by p. We will show that later. It's this guy, right? So this one, and you are thinking it's taking derivative with y tilde. Y tilde is here, right? This one doesn't depend on y tilde, so you move this guy to this guy, to here, right? So basically, this is the formula. You move this derivative to this guy. Okay. After that, what do? You turn this a log. Basically, this is what you have. You turn this in a log. This trick you see that many times because policy gradient in the previous one, like score matching, we have done it denoise score again. So this one you divide by p, you multiply p, and divide by p become log. Okay. So let's look at it. Now you have this guy and divided by log. Okay, so now what it is, right? So if you think about what it is, it's actually let me okay, let me show that. So basically, I think that you divide by p, you divide by p. Yeah, actually, from this guy, right? Now you divide by p here. This one you also divide by p. So this is basically this formulation becomes this guy. This guy, the key thing is how do you interpret this guy? This is actually needs a little bit thinking. The interpretation of this guy is this is a base rule, right? So if you look at the base rule, This one is when you generate data and noisy data. Pi tilde is y tilde is noisy data. Y is clean data. When you generate these two, divide by y tilde, which is noisy data. Therefore, from probability point of view, it's conditioned on the noise your condition in y. So it's a base rule. Reverse that, which state as this guy. This guy says because of this. This coming from here, right? So basically, I'm just saying this one just divided by p comes from here. Divided by p, and now the interpretation, this one is base rule. Base rule is condition on y tilde. And you're taking expectation of this. Okay. So this one, probably I will state a little bit of thinking about this. This is a part of, it's a probability. A little bit of calculus here, right? And then this one is base rule is a probability. It's how do you learn statistical probability? You just say this is a joint distribution y tilde divided by y tilde is a conditional distribution of y given y tilde. Okay, so basically, and if you write in form, it's a conditional y tilde. It's divided by y tilde. It's a conditional distribution, and then you take expectation of this guy in the conditional. Okay. The main thing is what does it mean? What does it mean is actually you implement a loss function, right? What does it mean? Maybe I will just say this, right? This is the general denoising. This one doesn't require it to be Gaussian. Later on we will do that Gaussian. But this is a general distribution about score of this guy to say it's condition of a gradient. It's a conditional score, right? This one you can think about is conditionals about y given clean data, conditioned score of y tilde. And this one is a whole score, right? Y tilde without a condition on y. This one is a conditional score on y. Basically, it states for the whole score, y tilde, is I will take the condition. So it's a reverse condition a little bit from y, but then I will take of this conditional score and take expectation. And how do you implement that, right? Implement actually conditional expectation from the standard statistics or machine learning is a conditional expectation is a regression. You can learn by regression. This is a score function. If you minimize conditional expectation, you can use this as target, this as your model. Model, you say whatever, S is a neural net with this target. And then and this model should be dependent on y tilde. That's all. And then you learn regression. This one gets you the conditional distribution, conditional mean. So this is a statistical interpretation of this, and we will give the specific example for the Gaussian. This needs some thinking a little bit, but basically it's a probability. So one need to think through. Okay, let's look at the Gaussian case. So for the Gaussian case, condition on the clean data, the noisy data is a Gaussian, right? So this is a Gaussian. You take log, and this is a constant we can ignore, and you have this guy, right? And you take the gradient with y tilde, and then then basically it's become this guy. So this is this square, and then become that. So basically this is essentially the score. And if you say what is y minus y tilde, right? It's a minus noise, epsilon. So essentially you are predicting the noise. You're predicting the difference of your clean data minus your y tilde is where you want to estimate your score. So basically this guy is this guy, right? This state around that for the Gaussian. This one is a minus of your noise. It's a clean data minus your corrupted data, so it's a minus of your noise. So denoise score matching with a Gaussian noise, try to predict the score is a minus of a noise and subject to some scaling. Expecting of a minus of a noise, right? And in the diffusion model, the original ones, they started to do the expectation of noise. Basically, it's a expectation of noise. Certainly, you also predict expansion minus noise. But let's say expansion noise is score times minus sigma square. So basically, this is actually what and then you can use that for denoising and so on. But anyway, score and noise has a relationship. The implementation is the following. The implementation, we will see that is actually just using regression. Basically, you assign a regression function y tilde with the input y tilde. Output is a vector field, and using this as target. The target is y minus y tilde divided by sigma square, which basically is minus epsilon divided by epsilon square. Epsilon is the noise, Gaussian noise. Learning score become a denoising directions leading to this denoising score matching. And denoising score matching is the method which is used in diffusion model. Diffusion model has either a denoising interpretation or score interpretation. They can be interpreted both. You see both in the literature. We are actually, because we were focusing a little bit more on the denoising side later on. So we do not say too much about the score, but actually there's very strong interpretation from the score point of view. Yeah, as well. We just a little bit mentioned. So for the for diffusion model, but basically this is a regression problem. So you won't have this guy, right? Because you are conditional expectation. It basically says following. I started with this is my data, uncorrupted data, clean data, adding a small noise to that, giving you a corrupted data, form this target, right? So basically, I'm creating data like this, epsilon, form this type. By the way, this target is minus epsilon, right? So it's the same as minus epsilon divided by sigma. Oh, actually minus epsilon divided by sigma. So basically, yeah. No, this one minus epsilon times the sigma, yeah. So basically, yeah. So basically, yeah, this is a formula. So essentially, the objective function is exactly regression, and it's a denoising operation. And the interpretation of this guy, of course, is the score of the noisy distribution. So this is a connection. Compared to the previous score matching method, right? So the exact score matching methods, of course, this is much simpler. So we are very simple. This is much simpler. Yeah, this one. Yeah. Key message. So we do not need the derivative of scores, which is good. We do not need the integration by parts. We do not need the everything, and we just have a more simpler algorithms which connect the score with that of noisy distribution with a regression target, which makes the learning much easier, much more stable. If you think about the minimax in the GAN, it actually can be a little bit tricky because the discriminator, if you doesn't learn well, I mean, then you will fail, right? So but here the score is easy to learn. It tells you when you have a noisy it's actually very easy to learn. You just have this one, and this one really doesn't have any tricky unless the sigma becomes smaller, too small, right? When sigma be reasonably large, this is good. When sigma is very small, then this one becomes unstable. Yeah. So that's the only thing. So, but then you can say, oh, I can do to a reasonably large sigma, not too small, and that's still okay. So basically, we only need the standard regression on the noisy and the clean. And this is, I mean, besides of the inference, right? Inference we will say a bit, but essentially, from learning point of view, this is probably one of the most important reasons. It's a simple learning objective, no tricks, and you can implement, you can learn such score well. For all the score matching, or later on the variation of that is flow matching, which people all further prefers, right? We will talk about that in the next 3 lectures about the diffusion model and also image and flow matching and so on. But generally, this is where it comes from in some sense. denoising score matching. Okay, and there is the interpretation of a diffusion model with a score as well. Here's the PyTorch code. Oh, of course, PyTorch is easier, much easier than the other PyTorch code, right? Other PyTorch you need autograd. Your also it's cheaper because autograd you have to do each direction, right? And if your dimension is large, you really need to simplify. You only have approximation. But here if you look at that, right? So yeah, it's basically this is just adding noise. This one is y plus epsilon. This is a noisy distribution. This is a clean distribution. This is noise, and the target is a minus noise. Yeah, minus noise divided by this. Basically, minus noise y minus y tilde, right? So basically, yeah, y minus y tilde, right? So this is the target, and the score will be model of this guy. So your input is the noisy distribution, and the conditional probability, the interpretation that is it's a regression target. This is a regression target, and then yeah then you're done. So yeah, it's good to actually understand this. You know, this is not too hard. It's the score matching itself is just for background information. People try to move away, but the denoising you can actually it's not that hard, and you probably can use other places. And then you do this guy, right? So basically you do optimizer, backprop of your loss, and step. So this is a simple training loop you can do for denoising score matching. And you can use, if you put a sigma small enough, right, you can use that to approximate your clean data distribution, right? This is what we want to do, actually, in our experiments. So here we just say, oh, let's put the different size of sigma to say how well the performance is. Certainly, the trade-off is the following, right? Small sigma, more faithful to your clean data. Your noise adding is small, so your distribution of y tilde is more faithful to y. But then you know it's a because of this one divided by sigma square, it can blow up. So you have more unstable formulation. Larger sigma, right? You have a less faithful, but you have a more stable. So therefore, you know, there's a trade-off. It's like a regularization with much smoother sigma large means more regularization effect. You're adding smoothing noise to your data, and it's a more stable estimation about your score, but smaller is more faithful. So right. Yeah, basically, you know, the same thing, right? So same thing as before. That's what we have done. Grab the same clean example with Gaussian noise, right? So this is the training. Trains a score of noisy distribution using this guy. So this is this code is I just showed that it's very simple code. And also it's much better than, I would say it's definitely much more preferred. You just set a moderate sigma. Ignore the difference of p sigma and p. It's much more friendly than the original score matching method. Compare the several noise level, because small noise closer to the, it's more faithful, but harder to learn because of a divided by sigma square, right? So you will blow up, something blow up, larger noise. Larger sigma, smaller, but farther from the original distribution, right? With a fixed sigma, you can use Langevin. Langevin doesn't care what you learn. It's just treating that as a sigma field. Just just a score field, then just keep running your algorithm, right? So then you can try to sample from that. Yeah, here is what it looks like. So yeah, we look at a different sigma, right? Sigma small. This is small sigma. Small sigma, if you look at the loss, is much. Actually, first the noise is larger, which is not unexpected, right? Because it contains a larger, but it's divided by sigma square. So it's much more, I mean, it's more jagged, right? It's a little bit more up and down, more variance. And then gradually larger noise, smaller, then even larger noise is just much more smoother. And the noise itself becomes smaller. So divided by sigma square, right? It's the inverse to the sigma square. So this one is okay. Looking at what you see here, right? So this is small noise. Small noise turns out not doing what, I mean, supposedly it's more faithful. The only problem of it's not looking more faithful is because the regression problem become harder, right? The same number of training parameters, and you are learning something which is very high variance, right? So you do not learn well. So basically, this is reflected. It's not learning well because of the score field doesn't learn that well. Yeah. So this is this for that. Although it's more faithful, supposed to be more faithful. Here is a more balanced. It's like you can think about sigma as a regularization, right? So this one, then you say, oh, what should be the sigma? That's diffusion model. It's always from very large sigma, go back to smaller sigma. So that's a diffusion model, right? And then you are essentially using then you have a high regularization gradually to smaller regularization. Then you go to fine. So here is this is a more reasonable sigma. This is 0.35, right? So this is 0.15, this is 0.07, and this looks better. And of course, it's a little bit larger than this because you're adding noise to your when you add the noise a little bit, right? The become lesser sharp, right? This one is even more noise, then clearly it's a lesser sharp. This one doesn't mean it doesn't learn well. Actually, if you say the score matching field, this one definitely should be probably the best learned score matching field because adding more noise, the regression target is smaller, right? It's less noisy. So this one. But here, if you look at this guy, this guy but because it's more faithful, so this one looks better. Only it's because it's more faithful. This one is less faithful. That's only reason. But actually, the score field it should learn better. And this one certainly it just tells you it already overfits. Oh, not overfits. It just it doesn't learn well because of that. So this is a kind of a comparison of these two, have different levels, and different levels is also important in the diffusion model, which we talk about next, and this one can be considered as a motivation of all that. So yeah, best sum here come intermediate. So that's trade-off, bias variance trade-off. You can think of bias variance trade-off. So here is what because we know the score field, right? So we just do a calculation, and this is what you learn, and yeah, and this is intermediate, and so on. Yeah, basically. So this is what it looks like. If you look at this, for this distribution, if you think about I think the other one has a better ratio. Right, so the exact score matching, right, for this problem. But this one is good enough. But anyway, so this is the experiments on this side. So flow fields, we do because each one has their own. Maybe I should draw both the choose versus learned. Maybe you should draw both, but here you just draw one. But this one is a smoother. This one I don't know. I mean, basically, yeah. Maybe I should basically this is the flow field which is learned for different. Maybe you should compare with both choose and the generated. Yeah. Here we didn't compare, but essentially it just tells you supposed to be more smoother basically when you're adding more sigma. So that's all I can say. Yeah. but here doesn't. I guess it shows somewhat. Yeah. So this, I don't know, that more smoother or whatever. Yeah. But definitely, supposedly this would learn better according to this. Maybe we will draw some other numbers just to say this one has to be learned better. This one is intermediate. This is most difficult to learn. Okay, finally, I just say this, right? So score matching versus denoising score matching, right? So just doing our comments. This is something at least a high level you should know about these methods. Score matching, I would not say this is that important nowadays. Maybe in some special application, if you know that, in some special application, probably you could do that. But in the general application, it may not necessarily is a needed one. Direct object on the model score, right? So targets the original data source, the score. It's an unnormalized density estimation problem. You can actually learn the unnormalized density, or you learn the score directly. So either you can use that to learn. Implicit form involve a second derivative of the energy function, first derivative of the score, right? So basically. Voice normalization, which is why it can be done efficiently compared with the maximum likelihood. Maximum likelihood is the method we don't know how to do that. Even nowadays, for the discrete, they can only do that for the discrete data, right? So like large language model, people always use them. I mean, if you can do maximum likelihood, I would say people, this is the default choice. This is the preferred methods. But all these are the other methods to say why we don't do that, because it's hard. That's the only reason it's hard. It's not because it's not good. For denoising score matching, denoising score matching is more of the current relevance because it's a relation to diffusion model, because it's a relation to flow matching. And we see this multi-level adding noise, right? I want to add a little bit more detail to the experiments. Maybe I'll do an update of the slides. But there's a notebook you can play with, and you're adding different noise level, and you see the difference. And certainly, it's a larger noise level. The problem is easier. So only thing I can say is this is a rule of thumb. Learn from noisy clean pair, and this is exactly the way you also learn diffusion model. So you come out of clean data, adding noise, predict noise, and that's the direction of your score, the scale of your score. Target the score of the noisy distribution, not the original data distribution. So this one also you have to know. So in case there's something you should high level remember, right? So it's once you do that, it's exactly get you the score of the noisy distribution. Yeah, this is targets. So it's a very simple target. It's a regression problem. This can be learned effectively, especially when sigma is not too small. Yeah, even in diffusion model, people try to prevent it to be too small. That one normally requires ordinary regression, no derivative. So this makes it a lot easier. Sigma trade-off fidelity and smoothing. This one we have these experiments just to show you, right? The point of that experiment, you can add in different sigma. It's like a regularization. You can make a trade-off. So yeah, these are roughly the high level you should remember, right? So the test or something more or less, at least in our the exams, they are more roughly high level. So roughly at this level, probably a little more detailed than this one, but this one is a good way to start. So in summary, score doesn't depend on normalization. So this is why a lot of current methods looking at this, including the diffusion model, they have a score interpretation, including the score matching methods, denoising score matching methods, and so on. Score can learn that. So this is a key advantage. And you can use a long join to generate, right? So once you do that, denoising score matching turns score learning into regression on noisy data, right? When score is learned, long-Giving dynamics can be used to generate samples. Denoising, actually, I just want to make comments. So because we are soon immediately moving to diffusion model doesn't use long-Giving dynamics. They use some different way. We'll talk about that later. But for this one is similar to the score matching versus denoising score matching, right? If you have a score treating that original, you use the long-Giving. Right? But if you are using denoising score matching, then you are thinking more about it's thinking a little bit more about the noisy data's score, and then you have a different way to do it. Essentially, it's a denoising, yeah. So, but basically, yeah, based on that, which will be the topic of next class. Okay. So yeah, I think that's all for today. Yeah, thank you.